SGSG, Stroke-Guided Scene Graph Generation. In this paper, we propose SGSG, a stroke-guided scene graph generation approach, to improve structured semantic understanding of 3D scenes. Using XR controllers, users can inspect point clouds and scene graphs anchored in space, and draw strokes to refine the semantics of both objects and predicates, thereby enhancing semantic scene graph predictions through real-time interaction. This addresses the limitations of traditional methods that rely heavily on instance-segmented inputs and provides an interactive solution for improving graph prediction when input data is coarse or noisy, which is common in practical point cloud acquisition. As shown in the video, SGSG enhances the accuracy and precision of scene graphs. We designed 3 types of stroke-based guidance to support semantic correction for different types of errors. Homogeneous prompting strokes bind multiple nodes into a single entity, unifying fragmented object semantics. Relation enhancement strokes refine the relationship between connected objects, improving predicate prediction. Ambiguous annotation strokes allow users to hint at mislabeled or ambiguous node semantics. They enable users to make local corrections that generalize to similar structures across the scene. These interactions are lightweight, spatially grounded, and leverage XR's natural support for intuitive interaction. Our SGSG is effective in diverse 3D environments, from indoor everyday spaces to outdoor public scenes. By incorporating high-dimensional guidance from the user's intuitive interaction, it highlights small objects or those merging with the background. Reduces prediction ambiguity. Improves predicate-level accuracy. And better preserves the integrity of large objects, resulting in cleaner, more consistent scene graphs. Here is the pipeline of our SGSG. It takes degraded geometry and user interaction as input, and outputs globally refined scene graphs. The first component is the Stroke Guidance Representation module, which captures user intent from stroke sequences by combining temporal and geometric features. Then, a guidance injection network blends this guidance into inference, enabling both local and global semantic correction. During inference, in addition to core losses, a set of intervention losses with consistency-repulsive and geometry-sensitive constraints are introduced to enhance correction accuracy and generalization. For training setup, we construct a lightweight dataset SG strokes, by augmenting 3 R-scan scenes, with stroke-based guidance and annotations for objects and predicates. SG strokes contains 291,000 strokes across 3 interaction types, paired with over 1,300 scenes. Noise augmentation further aligns it with natural human interaction patterns. We compare our SGSG with 3 state-of-the-art methods. With the cross-modal method joint SSG, style semantic errors occur. Shower curtains are misclassified as curtains, and due to occlusion in the 2D assisted input, some supporting predicates are mismatched. With SGFN, fragmented point clouds perform suboptimally after semantic fusion. The toilet is recognized as a chair, and walls are separated into multiple segments. 3D SSG, which lacks reasoning aggregation, shows even larger deviations in object-level predictions. In contrast, our SGSG, guided by user interaction, successfully corrects mismatched labels, merges scattered parts of large curtain objects, and shares corrected stylized objects across the scene, from toilet to shower curtain, while also achieving better global predicate propagation. Here is another example. With joint SSG, spatial limitations of 2D supervision cause predicate confusion between the cabinet and walls, mixing up foreground and background. SGFN misinterprets fragmented point clouds due to missing geometric cues, and fails to infer non-same-part relationships. 3D SSG faces similar problems, with even more predicate-level errors. In our result, user guidance helps cluster fragmented labels into a chair, reduces ambiguity, and disentangles foreground-background relations through the hinting stroke. SGSG also enables generalization to predicates unseen during training. We design a user study to evaluate the efficiency, accuracy, and task load of our method. The task involves navigating the scene and correcting erroneous semantic labels. Under different conditions, users may use either stroke guidance or hard correction. Here is the visualization of the accumulated trajectories and action coordinates for all conditions. The number of required actions of our SGSG is significantly reduced, which also brings a significant user interaction time reduction. Our SGSG reduces overall task load, showing significant improvements compared to 3 control conditions. For more details, please refer to our paper. Thanks for watching.